rate laws that we discussed in the previous video, also called differential rate laws, relate the rate of a chemical reaction and the concentration of its reactants. And this equation represents your basic rate law, where the A and B in brackets are molar concentrations of two of our reactants, A and B. K is the rate constant, and it is specific to the reaction and varies with temperature. And M and N are reaction orders. They can be positive, negative, a fraction, or zero. Integrated rate laws, which is what we're going to talk about in this video, relate the concentrations of reactants and time. Integrated rate laws are very useful for determining the amount of a reactant or product that will be present after a certain period of time, estimating the time required for a reaction to proceed to a certain extent, or determining half-life. We'll get to that in a bit. Integrated rate laws are derived using calculus, but we don't need to do this in AP Chemistry. Our rate law equations are given to us on the AP formula sheet. Let's take a closer look at them and talk about how to use them. So let's start with our basic rate law here. If you were to use calculus and to integrate this, you would end up with an equation that you could rearrange into the format used on the AP exam here, where the bracketed A with a subscript T is the concentration of A at any time T, and the bracketed A with a subscript O is the initial concentration of A, and K is what we call the first order rate constant, because we're looking at a first order rate law. So how do we use first order rate laws? Well, if we know the initial concentration, we can use the integrated rate law to find the concentration after some period of time. If we know the initial and final concentrations, we can find the rate constant. And we can do this by rearranging the equation to solve for what we want and then plugging our numbers in. But we can also take this equation and rearrange it into a very useful form to get something that looks a lot like a linear equation. Y equals mx plus b. And if we were to plot the natural log of the concentration of A versus T, we would get a straight line. And as you can see, this line has a negative slope. And we can use this information to determine if a reaction is first order. In other words, if you see a graph like this one, where the natural log of the concentration of your reactant is on the y-axis, and time is on the x-axis, and you get a straight line with a negative slope, this is a first order reaction. Memorize this pattern because you will see it on the AP exam. Now, I want to make sure you don't get confused because there are a couple of different types of graphs we've been looking at for first order reactions. We've seen this concentration versus time graph on the left before. And it's pretty intuitive that the more time that passes during a reaction, the lower the concentration of your reactant is going to get. Well, this graph is different from the integrated rate law graph we're talking about now. Instead of plotting the concentration versus time, we're plotting the natural log of the concentration versus time. And we'll always get a straight line when we do this for a first order reaction. Here's an example. Show that the data below can be represented by a first order rate law by graphing the natural log of the concentration of hydrogen peroxide versus time. Then determine the rate constant for the decomposition reaction based on this data. We take this data and we plot the natural log of the concentration of hydrogen peroxide versus time, and we see we have a straight line with a negative slope. And this is classic for a first order reaction. Now, if we want to find K, we take the negative of the slope of the line. Now, look at this form of the equation again to see why this is the case. We've put the equation into y equals mx plus b form, and negative k is m, that's the slope. So k is the negative slope, and since the negative slope is the change in y, over the change in x. The change in y is the change in the natural log of the concentration of the reactant, and the change in x is the change in time. To calculate k by using the slope, we could pick 2 points on the graph and use the x and y values to calculate the slope. Or we could go back to our data table and use values from 2 different trials and plugging those into the equation. So let's go ahead and take some data from trials 1 and 5, and we're going to put it into our equation. And we crunch our numbers and simplify, and we see that our k is 0.116 h to the negative 1. We don't see h to the negative 1 as a unit very often, but this is correct, and this is why it's important to keep units in your calculations. Let's take a look at second-order integrated rate laws. These tend to be fairly complicated, so in introductory chem courses, we usually focus on the simplest form of a second-order reaction, where there's only one reactant involved. So let's start with a second-order rate equation for a reaction with only one reactant. If you were to use calculus and integrate it and rearrange it a little bit, you would get this form of the equation, which is on the AP exam equation sheet. Notice that we can also rearrange this equation to be in the form of a linear equation. Y equals mx plus b, where m, the slope, equals k, the second order rate constant. Now, if we plot the reciprocal of the concentration of A versus time, we're going to get a straight line with a positive slope. And this is classic for a second order reaction. Memorize this pattern since you may be asked to identify it on the AP exam. Let's look at an example problem. The reaction of butadiene gas, C4H6, to yield C8H12 is described by this equation. This dimerization reaction is second order with a rate constant equal to 5.76 times 10 to the negative 2 liters per mole per minute under certain conditions. If the initial concentration of butadiene is 0.200 molar, what's the concentration after 10 minutes? Our strategy is going to be to use the second order rate equation, which we can get from the AP chemistry equation sheet. We've got 2 different forms of it. Use whichever one we prefer. I'm going to use this one, but you could use the other. And I'm going to swap in the formula for butadiene for A. We'll substitute our values in, and with a little bit of algebraic rearrangement and simplification, we see that at the end of 10 minutes, the concentration of butadiene will be 1.79 times 10 to the negative 1 moles per liter. If we rearrange a second order rate law to be in the form of a linear equation, this can be very useful for helping us determine the second order rate constant. If we plot 1 over the concentration of A on the y-axis and T on the x-axis, we'll get a line with the slope of K. So see a graph like this, find the slope of the line, and you got your rate constant. Now let's talk about zero-order integrated rate laws. We're going to start with the differential rate law for a zero-order reaction. Rate equals K. We recall that a zero-order reaction exhibits a constant reaction rate regardless of the concentration of its reactants. These tend to happen only under certain specific conditions. If you use calculus to integrate this equation, you're going to get this equation from the AP formula sheet, and we can rearrange this equation to get the following linear equation in y equals mx plus b form. If we plot the concentration of A versus T for a zero-order reaction, we're going to get a straight line with a slope of negative K and an intercept of the initial concentration of A. Let's do an example. Given the plot on the right, graphically estimate the zero-order rate constant for the decomposition of ammonia sitting on the surface of tungsten. The lower graph is the decomposition of ammonia on silicon and quartz. The straight line in the ammonia versus time graph indicates that the decomposition of tungsten is zero order. However, it's not zero order in silicon dioxide. To find K for the reaction on tungsten, we calculate the slope of the line, and we can use the linear version of our zero order integrated rate law equation. And here we see that negative K is the slope of a line. Well, we can pick any 2 points on the line to calculate the slope, but it tends to be easiest if we use the first and the last point. Negative K equals delta y over delta x, or K equals negative delta y over delta x. It doesn't really matter, but to solve for K, we're going to plug our numbers in and simplify, and we get 1.3 times 10 to the negative 6 moles per liter per second. We can distinguish what type of reaction we have by graphing our data in different ways. If we graph concentration versus time, this will be linear if we have a zero order reaction. If it's not linear, it's not zero order. If we plot the natural log of the concentration of A versus time, and we get a line, then we know it's first order. If we graph the reciprocal of the concentration versus time, and we get a straight line, we know our reaction is second order. Remember that you are given all of these integrated rate law formulas on the formula sheet. And they are in order: zero order, first order, second order, from top to bottom. And all of them can easily be rearranged using algebra into that linear equation format. And this can sometimes be useful, as we've seen. In summary, the order of a reaction can be inferred from a graph of concentration of reactant versus time. And if a reaction is first order with respect to a reactant being monitored, a plot of the natural log of the reactant concentration as a function of time will be linear. If a reaction's second order with respect to the reactant being monitored, a plot of the reciprocal of the concentration of that reactant versus time will be linear. And the slopes of the concentration versus time for a zeroth, first and second order reaction can be used to determine the rate constant for the reaction.